Ya, porque llegaron tarde. ¿Era la tarea? ¿No?
Llorando.
Nada más por gusto, ahora sin excusa llegaron tarde. Muy bien. A ver, vamos a dar. Muy bien. Antes de que se me olvide, porque se me ha pasado comentarles, aparte del libro que estamos llevando, ese es de referencia tal cual, pero hay otro par que pueden ver, este es el de árbol. Se me ha pasado. En mi página, en la sección de la clase, ahí les puse el nombre, ¿de acuerdo? De este texto. Sobre todo cuando empecemos a trabajar con formas diferenciales y campos vectoriales, es una muy buena referencia. No aborda el hecho de lo que hemos visto de variedades y subvariedades, pero para trabajar con funciones suaves y diferenciales está muy bien. El otro libro que no tengo, porque creo que ya no me lo regresó ningún estudiante, es uno muy pequeño, también ya viejo, el de Milnor, el de topología desde el punto de vista diferenciable. Ese sí aborda lo que estamos haciendo en este inicio de la definición de variedad y todo lo demás. Entonces, están esos. Muy bien, entonces vamos a ver el tema que se llama subvariedades. Okay, so we're going to see submanifolds. But also this will give us many examples of manifolds as we know it. So it is important that it is a subset of a manifold, but at the same time, we will see examples at the end of the class where we will see new manifolds that we haven't seen before. So before going to the details, so we have our tree. We know that that's a three-dimensional manifold. And in our tree, you can look at the XY plane. So we already know that R2 is a manifold, but this one here is inside R3. And just keeping it in lower dimension, this is the prototype locally of how a submanifold looks like. So on some level, you are free to move. In this case, you have 2 dimensions to move. And there are other dimensions of the ambient manifold that you cannot move there. In this case, you cannot move up or down in the Z direction. You are restricted only to the X and Y plane. So that's more or less what's going to happen. So this is, roughly speaking, we will make this precise later. You have a manifold M, you have a point and you have a chart on your manifold. This is U. S is a subset of the manifold, and that's what you would like to make into a submanifold. So all of this is U. And the green part is a subset of N that we would like to make a precise statement of a submanifold. So that means that locally, it is possible to find a chart such that only on a few parameters, not all of them, you can describe this yellow path here of S. Okay? So we're going to impose local conditions on S in order to regard S as a submanifold. It will be given in terms of the charts of the ambient manifold M. Okay, so I consider a manifold of dimension M, and I take any subset, and the whole idea is to make S into a manifold, so to speak, but in this case, a submanifold. So it's going to be called, right now we would call this a regular submanifold of dimension K inside of M. M is our universe. And we're going to impose only local conditions. So at every point, at every single point of S, you can find a chart. Charts here, we only have it on M so far. So you are able to find a chart. We will write it this way, such that when you restrict the chart only on S, this is what I drew here, restricted to that subset, the subset of S inside of U, you can describe it by the rest of the coordinates. The first one are fixed. The first one are free to move. And the last coordinates corresponds to the 0. Okay, this is just for some convenient notation. I decided the last ones to be 0, like in this space. This direction is 0 for this set, right? When I move on S inside of U, I'm moving here on the image of the chart. Okay? So I have N minus K restrictions. You cannot move there. And that's why also here you have a K. So you are free to move in the first K directions, and in the last ones, you cannot move. So again, it is just a convention that on the first ones, you can move. Okay, so this is what we call a regular submanifold. It is a local condition. On every point of S, you can find a chart like this. If you can do that, we will call that a regular submanifold. A chart like this, with these conditions, we will call it an adapted chart. Okay? And also, we will restrict the domain. The domain now of the function phi will be only on S. and it would take values on Rk, the first k entries. Okay, so this is what we call a regular submanifold. So I can find a chart of the ambient manifold M such that the point of S inside of U can be described by the first k entries, and the rest are zero. Okay, again here you can see the advantage and maybe something that was very hard at the beginning, that an atlas contains every possible chart. So remember that M is a manifold, so we have a fixed maximal atlas, and the maximal atlas contains every compatible chart, right? For instance, let's say if you find a chart that these initial conditions instead of 0 equals, I don't know, 5 or 1, because it is a maximal atlas, you can make it to be 0. So they're just saying that you're on a different level. Instead of being at level 0, maybe you are at level 5. So this is just a normalized condition, and we can do it because the atlas has every compatible chart. So let's see examples. So for instance, if I have R2 and I take S to be the y-axis, so this is S. We claim that S is a regular submanifold. That means at every point, we must be able to find a chart with this condition. Can you tell me which chart works? What is the chart that you will take here? What is U? And let's take the standard chart, right? R1, R2. So U intersection S. So you are required to have R1 must be 0, right? And R2, whatever. Okay, so, no, I'm sorry, it's the other way around. Sorry, that's a mistake. Oh, no, right. R1, sorry. R1 is 0, and R2, whatever. You're moving in the vertical axis. So the standard chart is an adapted chart for this S. Any questions here? Okay, let's do another example here. Again, I would like to have R2. And now my subset is going to be the unit circle, center of the origin. So it is right here. And I would like to show that S is a regular submanifold. Okay, then, so let's take any point. I would take this. Any ideas of a chart that we can take here?
Like the two charts that we were using. After all, we use send the points to the line, right?
So, what is U, Jesus?
Like the entire circle minus 1 point, probably
No, no, but
1, 0, for example.
no. U has to be a chart of R2 of M.
Sí, cierto, sorry.
I want a chart in
Sí,
M,
sí, sí.
and then I have to intersect. So, what you were saying is when we know that the circle is a manifold and the charts of the circle. Okay, then, there are different ways of doing this. I'm going to use the polar coordinate charts. Okay, so you have here, sorry, X and Y. So let's say U is going to be all of the plane, let's say minus this line, okay? Okay, now what about phi? So I'm going to use uh, polar coordinates here. So I need to give a phi from U to some open set in R2, right? Uh, so this is X comma Y. So it is, oh, I'm sorry, the square root of that. And I don't remember the correct entry here. Is it just tangent? Well,
I, be- I believe it's arc tangent.
arctangent, and 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 then also I have to maybe make U smaller to avoid the zero. Arctangent of y over x or x over y?
Y over x is
Y over x. So we need to make U smaller. So let's say only upper half plane, just to make phi well defined. Oh, no, sorry. The problem is in X, right? The problem is in X, not in Y. So X. So I'm making my U only this open set, right? Just to make sense of this. And you see that under this map, all of you sorry. So this is R, this is theta, R between 0 and infinity, right? And theta is going to be between minus pi and pi, right? So let me do this more carefully here. Like this, right? Now, let's see what happens with S that it is on U. This is S, and on U, I will be at R equals 1. Right? So here, this is an adapted chart. Instead of 0, I'm taking 1, right? This is R equals to 1, right? If you want to make it more precise, we can shift everything to 0 if you want. Like this if you want, right? So now with this, making the R entry 0, you're describing all of S in U. So again, 0, 1 is just any parameter, any value. It's not important that it is 0 here. What is important is that some entries don't move and the rest move freely, like what you have here. Right. Any questions here? So again, that's the good thing that M comes with a maximal atlas. So it contains lots and lots of shards. The canonical one doesn't work for this example. The one that we need to choose is basically the one given by polar coordinates. So again, the whole idea of this concept that we have seen, regular manifold, is that if you move in S, then there's a shard where you move freely in some direction, you have no constraint, but some other directions are constrained to be 0 or some constant. Okay, so this is done for this example. I want to cover another example. Well, first, are there any questions here? Okay, so let's move on then. Let's see another example on our 2. And now I'm taking S to be this set. Do you know what S is? You have seen this curve before. Right, so you are between 1 and -1. And then you come like this. As you approach the y-axis, it fluctuates more, goes all the way up to 0 and 1. Okay. Now do you remember why have you seen S before? What are the relevant topological aspects of this example? When you were studying this example?
It is connected but not that connected.
So this is connected, but not that connected. It goes like that, right? Now, so far, what I have drawn here is connected. But then what you do is, what is happening on all the points here? That's an accumulation points of S, right? So let's consider those two. So S is going to be that curve, the union of those points. Very good. And then now this S is exactly an example that it is connected, but is not path connected. Okay, basically what we have added is the closure of S. Right? Okay, and usually the problem arises on points on this vertical segment. If you zoom in, no matter how small you make the ball center at a point there, you will always have vertical lines. Okay? That's the issue when you see this example related to connected and path connected issues. So if you take any point here on outside that vertical segment, you can find a chart such that this will be the zero set of something. That's no problem. Basically because at any point, you can find a neighborhood and you only have this. And then this basically corresponds to making x0 or y0. However, the same issue that you know also fails here. If you take a point on the vertical aspects of the vertical segment, take any point and take any neighborhood. It doesn't matter if it's very small, you will have many vertical lines like this. And this local picture shows you that S inside U doesn't look as the vanishing of some coordinate. You have several vertical lines, always. And that's exactly what you study by the points of the vertical segments are accumulation points. So this is an example that it is not a regular submanifold. You cannot find adapted charts on the points on this vertical segment. On the other points you can, but points there do not admit any compatible chart. Okay? So S is not a regular submanifold. Okay, so we have studied examples when you have some manifolds, when you don't have some manifolds in R2. And remember, in order to be a regular submanifold, it's just a local condition. At every single point, we require a chart with some specific conditions. Now, what you expect is exactly what's going on. A regular submanifold is a manifold itself. So this way we will have more and more examples of manifolds, as we will see later in the class. Okay, so I have S, a regular submanifold. Remember that this is only one condition, that at every point you have some requirements. It's a local condition for this. So, okay. So now, we consider the set of all adapted charts. So U was a nice chart on M, and then I restricted. I have an adapted chart. This is the notation of the chart in M restricted to U intersection S. Then the claim is that that collection is in fact an atlas. And now then S is a manifold. Right? So we conclude that S is a manifold every time that S is a regular submanifold. So that's why we are going to have new and new examples of submanifolds. Right? Any questions about the statement of this proposition?
With adapted charts, we just mean like the restriction, right?
Right. So I have the nice chart from the definition. And then what I do, this function is the same. And a point here is precisely, well, no, this is not correct. This is in RK. And then what's the relation with the original? Because it's RK and then zeros, up to you have n entries. Right? Or, yes. And you know it because of this. So I have a smaller domain and I have this, right? Jesus?
Yes, thanks.
Now, yeah, like, let's see these two examples. So S has a subset of the manifold. It doesn't have to be open. Here you have this example. This is not open in R2. This is not open in R2. Now, the chart that you take is open in R2. And S has a subset. It has the subset topology. So this part here, this intersection S intersected with U is an open set on S. This is an open set in S. Okay, so I take my collection of adapted charts restricted to S. And the claim is that we have an atlas, and so S by itself is a manifold. So we must prove that S is a manifold, okay? The first definition of a manifold are just topological conditions. Do you remember those?
Can you repeat that?
Sorry, come again?
Can you repeat the question?
Oh yeah, what are the topological conditions on a space to be a manifold? First, the topological conditions.
Second concept,
Right?
Hausdorff and locally Euclidean.
Right. So those three conditions, well, not those three. Those three conditions are satisfied for subsets, except locally Euclidean. Second countable, if a topological space is second countable, any subset it is. Also Hausdorff. Locally Euclidean, not so much. For that, we use the concept that we have the adapted chart. That locally, S looks like some RK. So the topological conditions, you can work it out, there's no problem. And going back to the previous example, that's why also this fails. Any small neighborhood that you take there is not locally Euclidean, right? You have several vertical segments. Okay. So basically, what we must do, so you already gave me the three conditions. Second countable, Hausdorff, and locally Euclidean, right? So here is where we use that condition about the adapted chart. What else do we have to prove in order to show that it is a manifold? So now we know that it is a topological manifold. What else?
The atlas, right?
Right. So first, we have this. I don't have any, sorry. The first condition for an atlas is just that it has to cover my space. And this we already do. We have this. Because S is a regular submanifold. So at every point on S, you have a chart like this. So there's no problem showing this. So this collection covers. What else? What is the other condition of the atlas that we must verify?
They are compatible.
Right. So we need to check that if they intersect, we have a C infinity map, right? I'm just going to give you the sketch of this. So I don't want to use that notation. It is not very useful putting phi sub s. So we need to put some dependency on the open set, right? U and V, not only S, right? So let's assume that U intersection V intersection S is non-zero. And for the proof, let's do a sketch of all of this. This is U, and this is V. And both of them have points in common with S. Like this. Right? Now, okay. And there's a map here that we know that it is C infinity. Now, this is a C infinity map. Then all that you have to do, you have to be a little bit careful because under phi of U, S is mapped here. And remember that that purple segment is not open, right? So it's not that you restrict this map to this and it is C infinity, because that set is not open. So you have to argue in a different way to conclude that it is C infinity. But that you can work it out by yourself, how to come up with that part. Okay? It is not, you just have to write down what is this function. Well, not, let me tell you here then. You are restricting that to a closed set, so you cannot argue that it is C infinity, but the one that you care is this one. That's the one that you care that it is C infinity. Okay? This function is going to be defined on some Rk, subset of Rn, and so on. Okay? You don't know that that one is C infinity, but you know that this is C infinity on all of Rn. Right? So basically it boils down to this result from multivariable calculus. If you have a C infinity function between Euclidean space, each coordinate function is C infinity. And then you're done. Okay, so regular submanifolds are manifolds on their own, but sometimes it is important to keep in mind that they are inside some bigger manifold. So this is nice and everything. We have a new way of creating manifolds. If I know that something has of manifolds, but so far, maybe we have to run into the same trouble But there is a very nice way of creating regular submanifolds. And this is what we're going to see now. And it is related to smooth functions. So consider a smooth function. I have two manifolds. Remember that we have seen the differential is a linear map between tangent spaces. And remember that we saw what is the definition of a critical point? We saw critical points only for a function like this. Do you remember what's the definition of a critical point?
When the derivative is equal to 0.
So we need to take a chart about the point, and then using those coordinate functions, we can take the partial derivatives. If all of them vanishes, then that is a critical point. Okay? But in fact, a critical point makes sense for general smooth functions, not only real value functions. And it is better to describe them in terms of the differential than on local coordinates. So it's a critical point if this linear map is not surjective. And that's precisely what Moises told us. For real value functions, if all of the partial derivatives vanish, then we don't have a surjective map at that point, right? Because we will have G basically what we were saying, that each entry vanishes. So in particular, it is not surjective because this is a one-dimensional vector space. So the definition that we had of a critical point for a real value function was that all of the entries vanishes. Okay, then, so that's going to be a critical point. The differential is not surjective. And a regular point is going to be something that when the differential is surjective. Okay? Very good. So we are describing points on the domain of the function. A point is critical if the differential is not surjective, and is regular if it's surjective. So it's either one of two. It's either regular or a critical point of the function. And something that it will be useful later on, we will not use it this class, but later, the rank of a smooth function is exactly what you expect. The rank of a function at P is the dimension of the image, right? And this makes perfectly good sense if you recall your knowledge of linear algebra. The rank of a matrix can also be defined in terms of the image of the linear map induced by the matrix. So that's going to be the rank of a function at a point. I go to the infinitesimal aspects, the differential, and it has to do with the image of that linear map. That will be the rank. So the rank will be between 0 and the dimension of n. That's the rank of a function at a point P. Finally, we have described critical points and regular points on M. And now here we define critical values and regular values. So a regular value means that it is the preimage of every point is a regular point. So that's going to be a regular value. And it is critical value if there's at least one critical point on the preimage. Okay? So in order to talk about a regular or a critical value, I look at the preimage of that point. If all of the points are regular points, I have a regular value. If at least one point is a critical point, then I have a critical value. So like the important aspect in this sense right now are the regular points. So let's see examples of this. So I'm going to consider the unit sphere, two-dimensional sphere. So I'm using the ambient coordinates, x, y, and z. And my function is the projection. So basically, I'm projecting to the y-axis, to the z-axis. That's my function. Okay? Now, if you take a point here between -1 and 1, the preimage is going to look like a circle. For any point between 0 and 1. However, for 1, the preimage is going to be a point, and for -1, the preimage is also another point, the south pole. So far, so good? So almost for any point, the preimage is a circle, except at 2 points. I have the north and south pole for 1 and -1. Okay, I'm not going to do the calculations directly. I have to look at this linear map in order to know if I have a regular point or a critical point. But let's use the geometry of our problem to decide that. Okay, then. Let's look at one of the circles. Take a point here, right? If you move in a curve along that circle, this vector field, that vector will map to which vector here? Remember that we have a way to compute this using curves. So I want to know this vector here, which is along that circle, where does it map to? So consider the curve, which is that circle. So you can parameterize this curve such that at point P, the derivative is this vector, this green vector. Okay? So you parameterize a little bit the circle, that it goes through that point, and the derivative is exactly the green arrow. Now, in order to compute this, using curves, now I use the function f to see what curve I have on the other side. And what is the curve that I have here? It is a constant curve, right? And so what is the derivative of a constant? It is 0. So this vector maps to 0. Now, if you take any other vector which is not in that one-dimensional set, this one or this one, the differential is not going to be 0. You will get some vector like this, more or less. In other words, what I'm saying here is that for any value, which is not 1 and minus 1, I have a regular value, because the differential is surjective. At this point, the tangent space is one-dimensional. So it suffices to have a non-zero vector, and we know that it is surjective. Now, well, up to here, any questions? So let's see what happens when C is 1 or minus 1. Okay? Now, in this case, you can actually argue without using the concept that you have learned here. Because you know that the value 1 is the maximum of that function. And minus 1 is the minimum. So the north and south poles are critical points. So those two are critical points because that's where you achieve the maximum of the function and the minimum. So that's one way of arguing that 1 and minus 1 are critical values. Also, you can think about the tangent space on the north pole, for instance. and any vector that you take here and any curve will be projected to the 0 vector. So you will have also this. So on the sphere, any point that is not the north and south pole is a regular point, and only the north and south poles are critical points of F. Any questions?
No.
Good. So let's move on then. I'm going to take the two-dimensional torus S1 plus S1, as we know it in our tree. And instead of laying flat as usual, I would put it standing in vertical position. I'm not putting any coordinates here, but just you put the donut, and let's say your function is the height function. Okay, so I don't know very well. Let's see if you are in a table that can be the 0. Maybe this is height 0. And I don't know, you can move all the way up until the height of the donut. So let's try to understand critical and regular point as well as critical and regular values. Okay? Now, let's argue as the previous example and see how far can we go. That point is going to be a critical point because it is the minimum of F. You cannot go below the table. So that's critical. And also this one here is the maximum. So you have critical points there. Hence, here you have a critical value, and at 0, another critical value. Now, let's consider this point here. Let's call this C. What is the pre-image of C? What does it look like?
It's like this. An ellipse.
Right. And we will usually say a circle, right? But that's right, an ellipse. So you have this, right? The same argument as in the previous example tells you that this vector like this map to 0, and any vector like this will be mapped to a non-zero vector. And since this has dimension 1, then what you have there is a surjective. Right, so here F from the torus to the reals. The reals one-dimensional. So that C is going to be a regular value of the function. Now, what can you tell me? Think of different values of C. when do you get something different than an ellipse? If you start moving C up and down, when do you get something distinct than a circle or an ellipse?
Somewhere around the hole of the torus.
Right? If I'm around here, I get this circle and this one, right? I get two circles. My image is not connected anymore, has two components, and those two are circles, right? And the same argument as before will show you that we have a regular value. What else? What else can you get? Only that, or there's something more special that we are missing?
At the base of the curvature of the circle in the torus. That should be the critical point, isn't it?
Right, so if you think of moving, let's say from 0, moving the value up, on the left-hand side, you have a circle. But eventually you have two circles, so there's a point when they have one in common, right? You have only one, and then 1 point in common, and then split it. So that's, let's say, around here. And here. In this case, you have something like this, and they have a point in common. Okay, so let's call this C1 and C2. If you are above C2, you have one circle. If you are below C2, you have two circles. And exactly on C2, they match into a single point. Okay, now what is happening there is that C, let's see, all of the points in this two circle, except the point in common, are exactly regular points. All the points in the purple curve are regular points, except for the point in common. This is a critical point. And also this one. And so in order to show that it is a critical point, you have to exactly look at the differential. You can work it out very well. I mean, if you want to do the differential, remember, think of this. And you have these coordinates in C times C. But let's think in a geometric way, what happened with the tangent at each point. What happened here is that the tangent space, it is completely flat, parallel to the XY plane. That also happened on the minimum. The tangent space is flat. So if you start moving to the other point, you can see that here and here, the tangent space is also flat. This more or less, you can argue this, what you know from calculus. The local picture here is something that you know very well, and it is precisely the saddle function. And you remember that the origin is a critical point of that. So locally, this and this look like this. And this example, you know it very well from multivariable calculus. That the tangent space is the xy plane there, exactly. Nice. Okay, so this was more intuitive than computation. But are there any questions on example 2? Great. So we have seen many concepts on this section. We look at the differential, we define critical points, regular points, as well as critical and regular values. And the way that these new concepts are linked with the first concept that we saw this class is because we can get submanifolds by looking at the preimage of a regular value. Okay, so if you take a smooth function and take a regular value, the preimage of that point is a submanifold. And moreover, you can detect what is the dimension. Right? So on example 2, those ellipses or circles are submanifolds, and that's true. This is not a critical value, pardon, that's not a regular value, it's a critical value, and the preimage is not a manifold, because at the intersection point, locally, it doesn't look like R1. It looks R1 and another R1 locally. So precisely, you must focus on regular values of the function. A ver qué pasó, Moisés. Mejor say it out loud.
Wouldn't C would have to belong to Rn in order for the F inverse to make sense?
Okay, hold on. So you're arguing about this?
Yes, in notation you have that F is from M to Rn, and there you have that F inverse is that C is in N.
Right, it's the preimage. Oh, no, sorry. So there's a typo here. Eventually, Rn will be N. This is what it is. C is in Rn. That's eventually this result will call on arbitrary manifolds. Yeah, so here Rn. Okay. And this n corresponds to the dimension of this manifold. Okay, then, so let's prove this. We We will see more examples of this result, which are more interesting than these ones, but nonetheless, these examples are a good motivation for critical points, critical values, and so on. Right? So just saying more about what Moises was saying, eventually we will replace this by an arbitrary manifold. Everything will remain the same, and here will be the dimension of that manifold. It's always the difference. Nice. Okay, so I'm going to do the proof just for R1. It is very, very similar in general, but we will do it only for R1. So I take a regular value, and I want to see that the preimage S, which is inside of M, is a regular submanifold. So far, for a regular submanifold, we only have the definition. We need to find a chart with some specific conditions. Okay then. I take any point on S, and I know that that point is a regular point by definition. Now, take any chart about about P. We are going to change this in order to make it a nice chart for S and P. So U is arbitrary because M is a manifold. Now, because P is a regular value, we know that the differential is surjective, right? So with respect to these coordinates, I know that at least one partial has to be non-zero. At least for one, okay? Because I'm assuming that, because from hypothesis, C is a regular value, P is a regular point, so the differential cannot be surjective. So at least one of the partials is non-zero. Let's assume that it is the first one with respect to x1. Okay. I want to show you what's going on more or less in terms of a picture. Now, again, I'm going to emphasize, we would like to find a nice chart. So we are dealing only locally about S. Now, see, you have a point in S. I didn't draw S here. And then, because P is regular, that map is surjective. So you have a linear map from this vector space, the tangent space, to a vector space here. So this is R. F goes from M to R. I know that that map, that linear map, is surjective. So that means that the kernel has dimension n-1. So here I have a linear subspace that it is the kernel of this map. The kernel is m-1 dimensional. I'm assuming that m has dimension m. And I only have one more dimension, which is mapped to the image. So the red subspace is the kernel. It's going to happen that the red subspace is precisely the tangent space to S. That's what we're going to be arranging, basically. Okay? So you know this from linear algebra. So basically the tangent space is the tangent space to the submanifold S. Okay, so let's continue to get the chart that we want. Right? So I have coordinates, and I'm assuming that at P, the differential with respect to x1 is non-zero. So I'm going to consider now this map. Remember that U in M is open. It's given by the manifold. Okay? Now, I'm going to consider F tilde. I wrote down N. So here I'm using that N is the dimension. I usually put M, but now this N here. Okay? Let me see, that's what I wrote before. No, sorry, yeah. No, I have M, that's correct. So the other is a typo. Okay, I'm going to define this function. I take any Q, and it takes this. Remember that my coordinate has M entries. I'm omitting x1, and instead I'm putting F. The rest are the same, are unchanged. I only replace the first one. Only the first entry is replaced by F. Remember that F is a real value function. Okay? This is just a normalization condition. You will see why. But it is basically F, the first entry, and then x2, x3, up to xm. I claim that this is a chart on M. Well, almost. First of all, it is defined on U and it is C infinity, right? Because we already know for the coordinates, and also F by hypothesis. So this is C infinity, And what about the Jacobian? If you take the Jacobian of this matrix with respect to the chart x1 up to xn, what can you tell me about it? The first entry, or even the first row, there's something that you cannot say very much. But you can tell me about the rest. What goes below?
The rest is diagonal, right? With only ones in the diagonal.
Because,
starting from the second column.
right, because we have already computed that, right? So I have zeros and then ones. And here, whatever, I don't care. It is irrelevant. What is important that I have zero here, zero, ones, and that. Then, what is the determinant of the Jacobian? It's going to be only this. And now here is where I use that fact. This is non-zero because P is a regular point, right? So I have a function defined on U that goes to Rm, and at what point the function has determined non-zero. That means that on a smaller neighborhood of that point, the function is at diffeomorphism. And this is what you must take from this. So the inverse function theorem comes here. So that's why it is so important, the inverse function theorem. So I have a function whose determinant is non-zero at one point. Locally, it is a diffeomorphism. So on a smaller set, maybe not U, but something smaller, open, that it must contain that point, I have a diffeomorphism. Now, one must check that this is compatible with the other charts, which is no problem because, so these are already compatible and the F is infinity. So that's going to be also belong to the atlas of M. And now here is very important, our definition. If I restrict this open set to S, that's the preimage on that U, what exactly do I get? Zero and whatever for any Q on that point. And that's exactly the condition that it is required for S to be a regular submanifold. So I get zero here because I did this. Otherwise, I will get the constant f of q, which is c. The same that happens with the circle and how we shifted the polar coordinates. That's the same function of this constant, just to get 0. So far, so good? So that's my adapted chart. In my definition, I have n minus 1 free entries. The dimension is n minus 1. So the key idea comes from here, like the inverse function theorem. You move things and everything will work because of the inverse function theorem. Any questions about the proof?
No.
Okay, so we will look at again in a few moments ago, but I mean from this, all that you can see is that it is not so important if I put R1 or any other manifold, basically. Of course, we need to use the right concept for regularity of a point. Okay, now let's try now more faster. We will go faster on the same problem, but let's replace R1 by Rn and mimic what we did before. So I have that map. I have a point here, which is regular. That means that the linear map is surjective. That's the mixture at the tangent space. Okay, note that this is a subspace. This green one is isomorphic, so that one you cannot make. The kernel is a subspace. The other one is any other complementary subspace. But the red one is fixed because it's the kernel. The green one is any other complementary subspace. Good. Okay, now, so around P, I take a chart x1 up to xn. Okay, I have it there. With respect to that chart, remember that this is exactly this, right? This. And I'm assuming that that map is surjective. So I have at least n vectors such that the map is non-zero. So I will make some arrangements. The image of this is a subset of dimension n. So I'm going to assume that the first ones do not go to 0. So I assume that those functions do not go to 0. Okay? This is the map that you take now. This is in Rn. And then you have the other entries. Remember that on U, we have the coordinates x1 up to xm. So I need to write it down. So now you consider the matrix, the Jacobian matrix, and everything will work. Okay, and now you will use the fact that you have you have a block which is non-singular, and that will help you. Okay, and the whole idea again is to invoke the inverse function theorem, so that this function will be a diffeomorphism in a smaller set, and then you're done. So this is the general statement. Function between manifolds, and the image is a submanifold for regular values. Note that this number is always greater or equal than 0, because we're talking about regular values. The differential is surjective. So you have a larger domain than codomain in terms of dimension. Okay? See? That's it. Right, so sorry about this. Also, our time is up, so what we will do next time are applications of this. And the idea is we would obtain new manifolds that we haven't seen before. So this result is very useful because so far, the only way that we can come up with manifolds was by definition. Find an atlas, and then that will give us the theory, a maximal atlas. So we have the atlas approach. We know that the product of manifolds is also a manifold. So that was another way of obtaining new manifolds. And the other one was open subsets or manifolds are also manifolds. So roughly speaking, those were the only ways to come up with manifolds. With this result, we will also have examples of manifolds. For instance, well, let's just finish this one. This is a basic example, something that we have already seen, the sphere. We know that the sphere is a manifold. We have seen that before by using an atlas of two shards. There's another way using Euclidean space and this map. To compute the differential, we use the standard shard on Rn. And for any non-zero C, any non-zero element here is a regular value. Because you see how the differential looks. So also for what we have seen before, the graph of that is a paraboloid. Only the origin is the critical point, is the minimum. So this way we have that the n-1 dimensional sphere is a manifold. So now a different way of arguing that spheres are manifolds when we view them as regular level sets. And now the other approach that we will see tomorrow is this one that we have seen it only as a group, but we didn't show that it is a manifold. We will see that tomorrow, right? And other examples that we have, they are pending there, that we have seen that there are nice examples, but we have not been able to show that they are manifolds. Very good. Any questions?
No, it's fine.
No? Okay, then, so I will see you tomorrow and we will continue with examples of this, applications of this result. Okay?
Okay. See you
See you.
tomorrow.
See you.